structure the talk today with a few simple messages. So the 4 simple messages are: climate models don't work. We're basing all sorts of momentous policy decisions on models that don't work. And secondly, we keep hearing about, let's stop climate change, we'll fight climate change, and climate will change. It has always changed. It will continue to change no matter what we do with CO2. I think that's obvious to most people if you haven't been too educated. Now, the third point I want to make is that, you know, when you talk about anything, you should always think about pluses and minuses. It's as they say, an ill wind that blows no good. And in fact, if you count up the pluses and minuses of CO2, I hope to persuade you that the pluses easily outweigh the minuses for many reasons, so it will benefit humanity. So no one should be ashamed of emitting CO2, and we all do. In fact, I have a little monitor here of CO2. I usually turn it on, so I'll do that right now so we can measure the CO2 in this room. I think you know outside, CO2 levels are a little more than 400 parts per million this year. They're slowly going up, about 2 parts per million per year. But we all breathe out huge amounts of CO2. My breath going into this mic is 40,000 parts per million. You know, it's 100 times what it is outside, and that's true of every one of you sitting here. So this room should be pretty full of CO2 by now, because we're all sitting here alive and breathing. So let me plug this in, see what we've got. So here's meter. Okay, here's my meter. You probably can't see it. You can hear it squeaking because it says this is an emergency. The CO2 levels are 1,700 parts per million. It's roughly 1,700 parts per million in the room. That's because we're all sitting here breathing. And what this is really designed to is to control air condition, you know, heating and ventilation. When this level gets high like this, it means that you're supposed to turn up the fan, you know, and get a little more air circulation. It doesn't mean that the air is dangerous. But last night at Chapel Hill, it was a huge auditorium, and, you know, the windows were open, and so we barely made 700 parts per million, but this is 1,700. So you're real champions here tonight. Everybody's very healthy. All right. The fourth point I want to make is that it really is immoral what we're doing to the third world, you know, with climate policies. I mean, we should be ashamed of ourselves in America and in Europe, what's happening there, all in the name of saving the planet. You know, it's just silly virtue signaling. It's not saving anything, and it's hurting a lot of people. So those are the 4 key messages I want to make, and then I want to turn to discuss some actual climate science to the extent that I have any time left. All right, so your message number 1 is that we're using models that don't work. So we're making stupid policy decisions on CO2, renewable subsidies, things like that actually do no good at all, and they really do harm. So all pain, no gain. So here's a picture that sort of summarizes the performance of models. This red curve is expensive computer models that are predicting what the temperature should be year by year. This is 1975, this is 2020. And there are some 100 models here. This was put together by John Christie from University of Alabama at Huntsville. And down here is what's actually observed with satellites and balloons. So we're making policy decisions on this red line, and this is what's happening. And you can see practically nothing is happening there, maybe a little bit of warming, but it's much, much less than the models predict. Here's another way of presenting the same facts. There are many, many papers like this. There's no dispute about this. So this is a histogram of model predictions, these gray bars, and the red bar is what's actually observed. So this is warming per decade.
Just going to tell you you're close to the edge.
Oh, okay. No, don't worry, I won't break. Yeah, and this is for, I guess, 1993 to 2012. This is a little shorter period. But again, you see the predictions are way high compared to the observations, which are these red bars here. So this is the same data really as this, but by a different research group. All right, so models don't work. Why are we taking them seriously? Okay, short message number 2 is there's no way we can stop climate change. Climate is going to continue to change, and it's always changed from the beginning of the world. It will continue. One of my favorite characters in history is King Canute. He didn't actually look like this. He probably had a black patch over one eye. He was a tough old Viking captain, and he managed to seize control of Denmark and England. But he knew a thing or two about flattery, so his courtiers here used to tell him, "You're such a great king, you can do anything. You can even control the tides." And he says, "Is that so? Well, set up my throne here, and if my feet get wet, you've all had it." And he didn't look like this. He looked much more threatening than this picture. Okay. But here's an example of climate change. This is a tree growing on the bottom of Fallen Leaf Lake in California. It's under 100 feet of water because the lake is full of water now, and it started to grow back in the years 1000, 1100, 1200, when there was a 2-century drought in California, so all the Sierra Lakes dried out, and so trees could grow on the bottom. So there was this enormously long drought. It makes the current drought, which only lasted 3 or 4 years, look very, very puny. But it could happen again. And I can assure you, whatever caused this drought, it was not ExxonMobil or Peabody Coal, Okay, third key message is that CO2 is not a pollutant. I keep hearing about carbon pollution. I don't know what they're talking about. It will actually benefit the Earth. So let's talk about that a little bit. I mentioned that our own breath is very rich in CO2. 4% is 40,000 parts per million. So when we breathe out, we're mostly breathing out the inert nitrogen. There's still quite a bit of oxygen when you exhale. You haven't used it all up. And there's water vapor because your lungs are moist, and there's CO2 because you're metabolizing. That's quite close, actually, to what comes out of a power plant. So if you look at what's in these stacks, this white stuff is steam. It's not smoke. It's not pollutant. It's simply steam, like Alice's breath here. And it's very similar to a human's breath. It's mostly nitrogen. There's less oxygen because you are trying to run an efficient combustion plant here. It's got more CO2 because you have to use it to burn the oxygen, use the coal to burn the oxygen, but otherwise it's quite similar to human breath. And a good modern power plant, whether coal or natural gas or oil, really puts nothing out except for these 4 gases here. You can strip out most of the sulfur, you can strip out most of the oxides of nitrogen, the ash, there's usually a little bit of mercury in coal. You can get all of that out. And so all that's left is this, which is the same thing as we exhale. So why that's a pollutant, I don't know. It's not a pollutant. Here's real pollution. This is Shanghai. Perhaps some of you recognize Shanghai. That's the Pearl Tower. That's the bottle opener building. You can just barely see the bottle opener on the top through all the haze. Here's some poor resident of Shanghai with a mask on. And Barbara and I have been there on days like this. Shanghai really does look like this. It's been a long time since any American city looked like this. And it's not because of CO2. It's because they're not controlling particulates. They're letting the farmers around Shanghai burn their fields anytime they feel like it. And so they're completely correctable. And the Chinese, to their credit, are gradually correcting this. But you see the same thing all over the world, in Mexico City, in Delhi. And it's not CO2. It's an environmental problem that will be corrected, should be corrected. This is the most modern coal plant in America. I visited it a year or so ago. It's in Texarkana, Arkansas. And we arrived on a nice fall day. It was in October. And from a great distance, we could see this stack, and you can see there's nothing coming out of the stack. So we were very disappointed. We thought the plant was not operating. But in fact, it just happened to be a dry day, so the plant is actually pouring exhaust out into the upper atmosphere here, but it's so dry that the water doesn't condense. And they've taken everything else out that you might be able to see. There's no ash, and they've in fact taken out all the sulfur oxide, the oxides of nitrogen, the mercury, and it's pristine clean around here. There's nothing lying on the sidewalks or on the road here. So you can build plants that really are clean, make clean electricity day and night, whether the wind is blowing or not, whether the sun is shining or not, whether you have a hurricane or not, they still work. Okay. The other major benefit of CO2, what I was implying before, is that we get all these benefits just from burning fossil fuel. We get reliable, affordable power from it, much cheaper than power from wind, much cheaper than power from solar. But CO2 also has this huge benefit on agriculture. This is a field of soybeans. I like to tell my friends down here that, in sort of liberal America, when you show this picture, they don't even know what this crop is. I've heard people say, is this marijuana, because that's... But soybeans is one of the crops that's really benefiting from more CO2. Soybeans is a classic C3 photosynthetic plant, and so it's actually starving now. It's malnourished with respect to CO2. If you put more CO2 in the atmosphere, it grows better. It helps to have good seed. It helps to be genetically modified like this so that you can get the weeds out. But the CO2 is a big help as well. This is an example of controlled experiments with a pine tree. This is also for the aficionados here, it's a C3 plant. And this was ambient at the time the experiment was done a couple decades ago. It was 385, and this is increasing amounts of CO2 over the trees as they grow. And you can see the enormous increase in growth as you add CO2. The average levels of CO2 over most of the Earth's history have not been 400 where they are today, or 280 at the end of the last ice age, but they were typically between 1,000 and 2,000. So plants are really adapted to CO2 levels measured in the thousands of parts per million, not a puny 400. You can already see, even in the wild, that the whole Earth is greening. I can't believe it when I hear news reports about desertification of the Earth. Exactly the opposite is happening. If you look along the Sahel, just below the Sahara, everywhere you look, it's getting greener. If you look at western U.S., it's getting greener. So especially in more arid parts of the Earth, western India, the Earth is getting greener. And in this particular study, they did everything they could to take out the effects of more precipitation or less precipitation. So this is a pretty good approximation to the effect of the CO2 increase from 1982 to 2010 on plant growth across the world. So CO2 is greening the world. Why is that a bad thing? It's a good thing. So let me conclude with my fourth major message is the immorality of forcing the third world, the undeveloped world, to do without fossil fuels, the thing that's made us prosperous and comfortable and have a wonderful lifestyle compared to 200 years ago. We're supposed to deny that to Africa, to India, to other parts of the world. It doesn't make any sense. And for example, here is cooking with biofuels in Nepal. And this poor woman, if you were to look at her lungs, they would look like a heavy smoker's lung. You know, she'll have lung problems by the time she's 40. Here's a biofuels plantation in Africa. This poor farmer says our livelihood was dependent on the farms, and the biofuel company has taken our farms. Yes, poor guy, he doesn't have a deed to his land, and they just ripped it off, you know, some fancy Brussels lawyer. Here is another farmer, 26-year-old mother of two, smallholder farmer, house located on land earmarked for a biofuels plantation. Occupied the land for over 100 years, no alternative land or compensation. So that's the righteous holy in Europe, you know. And there are people like that in our country too. Oh, those are the four messages. I hope you remember them. And now we're going to talk a little bit about science. So we're switching gears. This is going to be less policy and more science, but I hope that will be interesting too. I think you know that we are living here on Earth. It's the third planet from the sun. We're on the Goldilocks planet. It's not too hot like Venus. It's not too cold like Mars. We get just the right amount of sunlight. And this, by the way, is not to scale left to right, but it is to scale with respect to the size of the Earth. You see how tiny the Earth is compared to the sun, or to Jupiter, or some of the outer planets. So we're entirely dependent on heat from the sun for our livelihood here. If there were no sun here, the temperature of the Earth would soon be dropped to the background temperature of space, which is only 3 degrees absolute, 3 or 4 degrees absolute, the cosmic background radiation level, you know, so it would, you know, it would be death. But we've got the sun to keep us warm. Now I think you all know the problem with solar heating, radiant heating in general, is if you face a fire, your face gets hot and your back gets cold. And the Earth has the same problem, that it tends to get very hot on the front and be cold on the back. Mercury has that in spades. So the front of Mercury facing the sun, you can melt metals with very easily, and the back is almost as cold as outer space because it never gets any sunlight. So we're lucky on Earth because we have the atmosphere that takes the heat from the sun-facing side of the Earth and it transports it all over the rest of the Earth. It's like a hot air heating system of your house. So the picture then, this is a picture from NASA. It's basically correct, although it's not correct in the details, you know, so this doesn't imply anything frightening about CO2, but they try to pretend that it does. But we're warmed by solar radiation. About 30% is reflected right back into space, so it never produces any heating at all of the Earth. But the rest is absorbed by the atmosphere and the oceans. That's what makes a nice warm day, makes this warm air that's coming in from the Gulf Stream today. And if all you had was heating, we would soon overheat. So you get rid of exactly the same amount, or very nearly exactly the same amount, by radiating to space, but at much longer wavelengths, you know, thermal radiation instead of visible and near visible radiation. So this is the basic physics of how the Earth works. And this deposited heat is carried all over the Earth by the atmosphere, by winds. And I think everybody knows that if you go up above our heads, it rapidly cools down. For example, I lived in Lenore when I was in high school, and Blowing Rock was, you know, only a little more than 15 miles away, but it was a kilometer higher. It was over 3,000 feet. We were just a few hundred feet in Lenore, and it was regularly 10 degrees cooler in Blowing Rock. So if you wanted to get cooler, all you had to do was go up the mountain and you could cool down. So there were lots of resorts built there 100 years ago for that reason. So the atmosphere cools rapidly as you go up. On average, it's about 6.5 degrees Celsius per kilometer, about 10 degrees per Fahrenheit per kilometer going up, until you get to 11 kilometers at our latitudes, North Carolina, New Jersey. Then the cooling stops and the churning of the atmosphere stops. So the bottom 10 kilometers or so of the atmosphere is full of air that's rising and falling, rising and falling. And it's like the hot air system of your house. It's transporting heat in such a way that it produces this rapidly decreasing temperature. It decreases because when the air expands, you know, the work that you have to do has to come from the thermal energy of the molecules, and so that's what does the cooling. Or vice versa, it does heating. When the air comes down, it gets hot. Now, on a grand scale, the Earth gets most of its heat around the equator. So if you want to know where is the Earth hottest, you ask where is the sun directly overhead? Well, and the sun is almost at the equator now. It's moving south on the 22nd of February, just 10 days from now. It will cross the equator. And so it's left behind a whole summer's worth of very hot ocean water, which is producing the hurricanes that we're having now. And it does that every year, year in, year out. Where the sun is burning brightly, it's depositing so much heat that large amounts of hot air go up to the very top of the atmosphere. And this is called the intertropical convergence zone. It's typically bands of clouds going around the equator, or a little bit north of the equator now because we've not quite reached the equinox. And you can watch this zone move north and south every year. And to supply this air comes down from higher latitudes, closer to the pole, and is deflected westward. And these are the trade winds. That's why hurricanes start out coming from east to west. They're being carried by the trade winds. But some of the air moves north, and that's deflected to the west. And that's why when the hurricane gets to our coast, it typically makes a turn and goes back out into the Atlantic because it's picked up by the westerlies. But it's been carried here by the trades. There's a lot of very interesting stuff here. So those of you who know about it, forgive me for simplifying, and those who don't, learn some more about it, you'd be interested. But in view of time, let me hurry on. This is a view of the Earth from a satellite. And this is called the Ceres satellite. It's clouds and energy, radiation. I forgot what it stands for. But it's designed to measure the amount of energy coming back from the Earth into outer space. So this is looking at visible sunlight coming back from the Earth. And this is on the 1st of October, 2002, soon after the launch of this satellite. It's still up there. It's still taking pictures like this. You can see there's a hurricane in the Gulf of Mexico, not so different from Harvey, actually. There's Florida. But the satellite also looks at infrared radiation coming out, the thermal radiation. If you, for example, have an intruder light around your house that picks up intruders, it's looking at this type of radiation, thermal radiation. And so what you're seeing here is how hot the Earth looks from space. So these regions where it's yellow or red are very hot. They're pouring infrared radiation out into space. This region where the hurricane is very cold. So this is practically not radiating at all. And that's because the hurricane cloud tops are so high. They're in that region I mentioned where the temperature is the minimum in the atmosphere. And radiation is a very strong function of temperature. So where it's cold, that is cloud tops, you don't get much heat going back to space. So the top of a hurricane is not doing very well in terms of cooling the Earth. On the other hand, it does shield the Earth somewhat from sunlight, so the sun doesn't reach the surface. So whether the shielding or the reflection of sunlight winds is a very delicate question, and that's one of the reasons that climate models are so difficult to get right, is how do you get this balance correct? Here you can also, so that's the intertropical convergence zone I mentioned. The sun has already crossed the equator on the 1st of October, so it's in the southern hemisphere, and so these are these big upwelling clouds at the intertropical convergence zone, which is in the southern hemisphere on the 1st of October. Okay, interesting stuff here. And here's a summary for the geeks in the audience of the Ceres radiation, satellite outgoing radiation. This is starting in the year 2000, soon after launch until 2013. And so you can see summer where the North Pole is warm, winter when the North Pole is cool, summer, winter, and you can see these very hot regions just pouring radiation out into space. And these are the descending branches of those big currents of air I mentioned. When the air comes back down, it's been stripped of water vapor, so it can get close to the surface and very hot and radiate with great efficiency. So these are the Hadley cells coming down. And you notice even though it's dark during the winter in the North Pole, it's still radiating energy out without any problem, and that's because energy is being transported to the North Pole even in the dark of winter and being radiated out to space. Even happens in the South Pole. It's not quite as efficient in the South Pole, but we're lucky to have this heat transport system. Now, when I showed you that heat radiation, none of that has anything particularly to do with CO2. Where CO2 comes in and where all the hysteria comes in is if you look at the colors of that radiation, you typically see pictures like this. So if you take the radiation from the Ceres satellite and you analyze it by wavelength, by wave number in this case, the number of waves per centimeter, there is a gap where the Earth does not radiate as strongly as it would without CO2. So that's the CO2 absorption band. Here it is over the Sahara Desert. Here it is over the Mediterranean. Wherever you look, you can see the effects of CO2. Over most of the Earth, it makes it harder for the Earth to cool. It's not radiating as much. But actually over the South Pole, it does the reverse. So the South Pole, cooling is being helped by CO2, but most of the Earth is being hindered. But the second message I have to say here is that this is a cloud-free day. All of these are cloud-free days. If they're clouds, you don't see CO2 at all. And I just showed you a picture of the Earth. Most of the Earth is covered, 30% of the Earth is typically covered with clouds all the time. So that part is not affected by CO2. And the other point is that you can see these huge effects of water. So this is water absorbing at long wavelengths, low spatial frequencies, water absorbing it, shorter wavelengths, high spatial frequencies. So the main control of the greenhouse effect of the Earth, this is the greenhouse effect in a nutshell, is really water vapor and clouds. It's not CO2. CO2 is there. It's quite striking. But it does not change very much as you double CO2 or you quadruple CO2. You would hardly notice the difference if I showed you a curve like that. We can't do the experiment, but you can do the modeling, and the models are pretty good. And so here's the picture that you should be familiar with. The sun shines down with shortwave radiation. It typically peaks around 0.6 microns, 6,000 angstroms, they used to say. And not all of it reaches the surface because the blue radiation goes into the blue sky, the beautiful blue sky, Carolina blue. And parts of the red radiation get absorbed by water vapor, so these are gaps due to overtones of water. But mostly the radiation does reach the surface if there are no clouds. This is radiation going back out from the surface to space. It's a little bit deceptive because a lot of radiation comes back to space from higher altitudes, from clouds, from water vapor and CO2. halfway up the troposphere or even into the stratosphere. But it gives the basic idea that getting that energy from the sun back to space is hindered by these molecules that are in our atmosphere, the most important being water vapor here, second most being carbon dioxide. Is quite puny compared to water vapor, but it's not negligible. There's a little effect of oxygen. Methane is even smaller, nitrous oxide smaller still. And the Rayleigh scattering is this beautiful blue, the Carolina blue. Thank God for Rayleigh scattering. So this absorption is due to the molecular physics. This is a CO2 molecule. It's linear. Here's the black carbon atom in the middle. It must be black, right? And oxygen on either end. This vibrates much like a xylophone bar, and it's that xylophone bending mode here where the carbon goes up and the two oxygens go down. That's responsible for most of the greenhouse warming of CO2. Yeah. It's actually 667, but I couldn't. All right. And close enough for government work. All right, well, here's what's happening to CO2. It's steadily going up. I mentioned to you we're maybe at 405 here in the year 2017. And CO2 typically goes up very strongly in the fall and winter and peaks, in the late winter. And as soon as the sun comes back to the northern hemisphere, it drops very rapidly by quite a large amount, 5 parts per million, 6 parts per million. Then it goes up again the next winter, down again the next summer, up and down. And what you're seeing here is the growth of plants in Canada and Siberia when the sun returns during the summer. And they grow so fast that they suck out large amounts of CO2 from the air. I actually see that in my own backyard. When I put this meter on my back porch, I noticed that the CO2 levels drop during the day, and as soon as the sun goes down, they go up again. So you can measure that yourself. It's quite easy to measure. And this is that same phenomenon on a grand scale. A lot of people also are not aware that we're in a CO2 famine now. So here we are at 400 parts per million. You can just barely see it on this scale. There's 1,000, so we're a little under half of 1,000, 400 parts per million. Looking back into the past, you can see that the typical levels are measured in thousands of parts per million. It's very, very rare that it gets as low as it is now. There was one period in the Permian where it may have been as low as now. That was 300 million years ago. But it's been 4,000, 5,000, 6,000 parts per million, so more than 10 times now. And the Earth flourished at that time. The seas did not acidify. The plants did not die. It was not full of deserts. In fact, it was a more verdant place generally when there was more CO2 than it is today. All right, so we're in the CO2 famine. So what's wrong with getting rid of the famine? I mentioned how poorly models are performing. I have to put in a plug for satellite measurements of atmospheric temperature. These are measurements done at University of, or at least analyzed at the University of Alabama, Huntsville by Roy Spencer and John Christie. And so this is from the beginning of the satellite era, 1979, until just last month. I downloaded this afternoon. The data for September isn't in yet because September's not over yet. But what you see here is that these are very small scales. This is 1/10 of a degree, 2/10 of a degree. And there's been very, very little change over this enormously long time. The models, the climate models, would have had a curve going up like that. I haven't put it on, but it's embarrassing to put it on. It's so bad. But there's some interesting things. This, by the way, this thing here, this spike is the El Nino in 1998. I'll say a bit about El Ninos in a minute. This was the El Nino we just came through, so we're coming out of an El Nino now. This curve is probably going to continue going down for at least another year. as the Pacific changes. So what's El Niños? Here is, oops, damn it, excuse me. Yeah, I'm not very good at this. Okay, what this is it's a picture of the Pacific Ocean. So here's South America, there's Mexico, North America, there's Florida poking out like an appendix. And here is the warm water on the surface of the Pacific, the equatorial Pacific. During an El Nino, the easterly trade winds that I mentioned practically stop for reasons that are not very clear. And so all the warm water that is normally piled up off of Indonesia comes sloshing back toward South America and Mexico and stops the upwelling, so the fisheries suffer. You don't catch a lot of fish during El Nino. And we get lots of rain in California. That's why the drought broke last year in California, because of the El Nino. Normally, we have the easterly trades blowing this warm water out toward Indonesia and Australia, so it keeps cool water off of our western coast, off of Mexico, off South America. And every now and then, like what is likely to happen in the next 6 months to a year, the trades actually intensify, and the normal condition is even intensified. The warm water is really pushed hard to the west. And so this is a cycle. It's rather irregular. Every 5 years or so, though, we have an El Nino, and it's usually followed by La Nina. But over longer periods of time, many decades, you can have many decades when you get more El Ninos and La Ninas and vice versa. And that has a big effect on our climate. Okay. I'm almost through. People worry about sea level here in North Carolina. I know David Burton has done a lot of studies on that, and my friend Steve Bodner has become a real expert, so after this we can talk to them. But this is a long-term record of sea level. This is the end of the last ice age, when a huge amount of water was locked up in continental ice sheets. Then they started to melt very, very rapidly, and this is a big scale over here. This is zero. This is 120 meters, 500 feet almost. 400 feet. And so there was rapid melting of the ice sheets. It was nearly over about 8,000 years ago, and there's been a very, very slow rise ever since. So indeed, sea level is rising, but it's rising essentially at the same rate it always has. Here's an example from what's believed to be a fairly neutral site in Denmark, where the land is not going up or down. You have to take the land subsidence or vice versa into account when you look at tide gauges. But these are tide gauge records in Slipshaven, Denmark. And here's the CO2 levels here in green. Here are the tide gauge levels here. If you can see any correlation, you're better than I. It's just not there. And there are hundreds and hundreds of these tide gauge records from all around the world, and very few of them show any correlation with CO2. Hurricanes. We've just gone through 2 big hurricanes. This is all of the hurricanes recorded since 1985. And you can see that we get hurricanes here where we live in eastern North America. They never get hurricanes in California. That's why there's still, redwoods and sequoias. They've long since have blown down. 1 or 2 hurricanes would do a job on them, but they don't get hurricanes. And then you get hurricanes in China, Vietnam, hurricanes in the southern hemisphere. There's a band along the equator where you never get hurricanes, and that's because hurricanes are partly generated by the air is able to sense which way the Earth is turning. So if you're at least 10 degrees north of the equator, you recognize that the Earth is turning counterclockwise, looking down on it. And if you're at least 10 degrees south, here at Australia, Southern Africa, you recognize it's turning below you, and it seems to be turning clockwise. So hurricanes rotate counterclockwise in the north. That's why the winds come in from the top right of the hurricane off the ocean. And it's vice versa in the southern hemisphere. Al Gore's never gotten that right. I'll show you a picture of Al in a minute. I've been trying to educate him. I got to know Al in 1993. He wasn't very smart then, and it hasn't improved. Well, here's landfalling hurricanes by decade. We just had 2 in this decade, 2008, 2017. In fact, the only 2 are the ones we've had this summer. So this is Harvey and Irma. And there were none before. So we had nearly 10 years with no hurricanes at all making landfall. But again, there is no real trend. CO2 has been steadily going up this entire time, and there's no correlation. That's true of all other extreme events. People say extreme events are increasing. It's nonsense. This is government data. This is mostly from NOAA. This is tornadoes per year. This is 1964. This is 2012. If anything, tornadoes are going downward. Big tornadoes, F3 plus. This is northern hemisphere snow cover. And I keep reading, people will never see snow again. We still see lots of snow in Princeton. My wife notices because she's a cross-country skier. And here's hurricanes, versus year. I think this is the entire world, not just hitting the U.S. But again, there's no trend. If anything, maybe slightly down, but basically noise. This is drought years. This is wet years. So, as I mentioned, climate changes, weather changes. That's the nature of the world we live in. But they don't correlate with CO2. So, okay, summer. And then we'll take some questions. So policies to slow CO2 emissions, they're based on flawed computer models which exaggerate warming by big factors, 2 or 3. If I wanted to be dramatic, I would say, 300 or 400%. But that's true. More CO2 is an overall benefit, so costly mitigation schemes, they're all harmful. They don't do any good at all. And in spite of these objective facts, alarmism continues. All you have to do is pick up the papers or turn on the network news, and you still see lots and lots of alarmism. This is driven by many motives. I'm just going to mention 2 or 3, and then I'll stop. One is virtue signal. There's Al. You see the hurricane's rotating the wrong way. When he put this melange together, somehow, he reversed the thing when he photoshopped it to make it look more threatening. But he seems to like that direction. Here's sort of a reusable bag. My reusable bag makes me better than you, because I don't use paper or plastic. We don't use paper or plastic either, Barbara. No. Barbara has a lot of bags like this, but they don't say this. And since Ian and I are Scottish heritage partly, I couldn't resist Rabbi Burns' poem here. Lord, bless thy chosen in this place, for here thou hast a chosen race. But God confound their stubborn face, and bless their name, what brings thy elders to disgrace and open shame. So that's Al Gore's prayer there. Holy Willie. And then there's politics. This is Mencken. Where is Mencken when we need him? The whole aim of practical politics is to keep the populace alarmed and hence clamorous to be led to safety by menacing it with an endless series of hobgoblins, all of them imaginary. Okay? So that's certainly the case of global warming. And then there's this one, crony capitalists, research empires. There's a lot of money involved. We spent last year close to $30 billion one way or another on, fixing the climate. So comparable to what we spend on NIH, for fixing our health. And so, various people have commented on this. Here's one from the Bible: where your treasure is, there will your heart be also. Who wants to give up such a deal? And this is from my favorite Russian poet. If anyone reads Russian, it sounds better in Russian, but the translation, if there happens to be a trough, there will be pigs. And this is Alexander Pushkin. Yeah, bless his heart. Pushkin was part black. His grandfather, I think, had been given as a gift, a poor little black boy slave given to Peter the Great. And Peter didn't know what to do with this kid. He didn't have any slaves, and so he adopted him. So he became Peter's adopted son, and Peter sent him off to military school in France, and he named him Hannibal. And so Hannibal, Pushkin's great-grandfather, became quite a distinguished Russian military man, and his descendants. Pushkin was the first one who was not in the military, actually, but he was a very good poet, so he picked the right profession. So I'll close with this comment from Schopenhauer: all truth passes through three stages. First, it's ridiculed. Second, it's violently opposed. And third, it's accepted as self-evident. And so the truth that CO2 is not harmful, but it's actually good for the planet, is somewhere between the stage of ridicule and violent opposition. So thank you all very much.